Good morning, afternoon, or evening, wherever you're joining this electronic recording. I'm Jake Walter, and today I'm going to talk about how we've implemented machine learning earthquake detection into the regional seismic network that we operate in Oklahoma as part of the broader USGS's Advanced National Seismic System. We've called this particular software package easyQuake, and I'm going to talk a little bit about how it's a pretty flexible turnkey machine learning driven earthquake sort of detection tool and locator tool, and maybe a jack of all trades. I'd like to sort of acknowledge all my staff at OGS who, obviously a seismic network is much more than just the algorithms we come up with. It really runs on the power of people who put this together. So kudos to them. Across the last decade, OGS has sort of built up the seismic network in a relatively ad hoc sense. And this was because the state experienced a surge in seismicity that's probably unprecedented in human history. And so you can see the wastewater disposal into the Arbuckle Formation, which really paced the earthquake activity. So these are the magnitude 3.0 earthquakes per month statewide here, tracking that, but with a little bit of a lag, tracking that wastewater disposal. And that seismicity continues to this day. So this is a snapshot from this evening showing the seismicity observed broadly across the state. And our sort of view of this is enhanced due to some of these advanced earthquake detection tools that I'll get into in a second. And the reason that we want to understand and locate and identify these small earthquakes is it helps us test sort of fundamental hypotheses related to fundamental questions about earthquake physics. How do faults start and stop, and why stress is heterogeneous in the subsurface and temporally varying. So identifying smaller and smaller earthquakes is particularly important in order to advance the science. But it's probably most important to broaden our sort of participation in the science in order to better inform the public. So that the public understands how to cope with these particular geohazards, especially in an area where these geohazards haven't been historically present. And so as part of our mission as a state agency and a non-academic research unit, we are particularly engaged in educating the community and educating the next generation on not only how to do science, how to be a science, but what to do in the event of these geohazards presenting themselves. And so one of the ways that we think that we can actually better inform the public is by identifying some of these smaller and smaller events. So these smaller and smaller seismicity, when you look at a picture like this, you can see that these are actually composed of very small clusters of seismicity that sometimes delineate linear features, which obviously this group knows as subsurface faults. And so we can sort of better broaden our understanding of the seismic hazard by better detection methodologies. And so this is where we present easyQuake, which is a way to actually take raw data, use a machine learning picker, associate those picks, combine all those events into a catalog that you can then is portable and flexible. You can do with that catalog what you will, but it's also reproducible, which we think is particularly important, obviously, when we're doing science. So we compute magnitudes, we can compute the first motion polarity, and then feed all that information into other types of formats that can drive that basic research. But we think that this sort of serves as sort of research goal in addition to that added goal of better informing that public with the most up-to-date information. So our philosophy is that all that information should go into deriving a QuakeML event file which we then feed directly into our SeisComp3 system, which we operate for the more real-time detection capabilities that are provided by that particular software. At the OGS, we actually run this nightly, that software nightly. So that's why it's not quite, we're not quite at the real time, but that's part of the sort of additional emphasis and additional development that we're putting into this particular package. So one of the things that we've added over the last several months is the ability to actually use not just the GPD, generalized phase detection picker, developed by Zach Ross, but to also implement the option to use the EQ transformer by Musavi et al. 2020. And so we found some performance gains by using EQ transformer in that it identifies a lot less false positive event detections. However, the GPD's false positive event detections also come with some degree of providing event detections that are detecting otherwise unreported events with EQ transformer. So this is by no means an exhaustive head-to-head comparison, but there are some slight performance gains if you're evaluating your performance based on the total number of events that you're detecting in a given day. So we get something like 85% of the events that GPD, using the GPD picker to drive the picker part of our earthquake detection, the EQ transformer only detects 85% of those events that we are able to detect with GPD, which is what we use at OGS. However, that comes with a performance trade-off, as I already suggested, whereas the EQ transformer is a fairly fast and efficient detection step. The GPD takes much longer. And obviously our associator, which is a fairly basic associator developed originally by Chen and Holland, 2016. The associator is relatively slow, dealing with a lot of false positive picks that it needs to sort through and make a decision about whether that's a real event or not. And I can elaborate on that step another time, but just to say that we are actually, by using the same associator, I think we can make some head-to-head comparisons about the relative performance of different pickers, rather than simply comparing whether a particular picker, which is obviously runs on a sort of deep neural network, whether it can recall test data and training data, but we can actually put it into some sort of real world scenarios and evaluate its performance accordingly. So like I just said, that we have implemented into the software, the production code, a choice of the picker. You just flag the picking step, whether you want to use one picker or the other. In addition, we've actually directly implemented a hypo-inverse calculation or event location calculation. And you can feed it a chosen velocity model or a default velocity model that comes with the code, and that actually updates the preferred origin within the Quake ML file. And again, just to emphasize, the Quake ML file, we broadly believe that it's the key for reproducibility in science, and also portability. So exchanging information between observatories, passing information along the product distribution layer at USGS. The Quake ML is the key for this sort of standard seismological formatting. And then we have a quasi real-time mode, but that's only in a testing phase and not really ready for public consumption. So this is a case study that we published on in our SRL paper that came out actually in early 2021. And we find that on the right-hand side, you can see a lowering of the magnitude completeness by 0.7 units on Oklahoma data. Again, this is our sort of real-time system. And you can see on the left-hand side where there's we're really detecting a lot of smaller magnitude events. By and large, the smaller magnitude events that would have been otherwise undetected are just helping to improve or lowering our magnitude of completeness pretty significantly. If you consider that we're using the exact same network geometry, it just has to do with the picking there. This is an example of an event that would have otherwise gone undetected if it were not for easyQuake. And this is a magnitude 0.7 event here. Here's a map view of the enhancement to the catalog. You can obviously see on the right-hand side these events that would have not otherwise been added to our catalog if it were not for easyQuake. We have some richer complexity in the central part of the state, in addition to areas where we have less dense station data. Finally, in Oklahoma, we run it daily. When the UTC day ends, that event information is populated into SysComp3, but it actually doesn't make it out into the world until an analyst is able to review that information. And as of May of 2019, we are an official member of ANSS, and so that data that is available in the USGS catalog is coming directly from OGS within our relationship as a regional network within ANSS. So this is a case study of actually unsupervised, just applying it to FDSN data from the Idaho area around the time of that large earthquake in 2020, early 2020 in Idaho. And you can see the significant improvement in the magnitude of completeness, just totally without doing much legwork there in order to produce an easyQuake catalog. So you can imagine that there's several use cases for improving early aftershock forecasts. Obviously, a robust forecast of the aftershock probabilities of having a large damaging event after a significant event is really related to some of the productivity values within this Riesenberg and Jones formula. And so obviously, robust statistics on the early aftershocks might actually improve early aftershock forecasting in the future. So our work continues on easyQuake. We continue to improve it and add new modules through time. Obviously, I've mentioned the real-time testing that's going on. There are quasi-real-time testing. And then one of the things that we're particularly interested in pursuing is improving some of our web mapping abilities and how are people actually understanding these catalogs and these earthquake sequences. So we've been trying to improve our visualization, plotting and statistics, and those will probably get added as sort of specific modules within the easyQuake in the future. So look for that. And obviously, we'd appreciate any feedback that you have for us going forward. Well, thank you very much.